Previous lecture I introduced certain criteria for estimation. That means, if we are taking an estimator, what properties it must satisfy. There are various other properties and we will be discussing them in detail. But now let me introduce the methods for finding out estimators, because it is all right to say that this estimator is unbiased or this is consistent, but how do we get them? So, I mentioned in the brief introduction to the history that the initial methods that were proposed were like method of least squares, the method of moments, the maximum likelihood estimation, etc. So, let me introduce these. So, in the least square methods, least squares, so here we assume that the data is obtained in the form of variables like x1, y1, x2, y2, xn, yn. For example, this may be related to certain relationship, like certain variables which are related in the sense that yi's could be the weights of the persons and xi's could be the heights, xi's could be the heights of the parents and yi's could be the heights of the offsprings, etc. So, there could be various kind of things where they are related. However, the relationship is to be determined in the form of a linear relationship such as yi is equal to say alpha plus beta xi. So, we assume that the actual observations will introduce certain error, say epsilon i's. So, the purpose is that we should estimate the parameters of the model, that is alpha and beta, in such a way that the sum of squares of errors, that is sigma yi minus alpha minus beta xi square, let me call it S. So, in the least square methods, we want to find out alpha and beta such that this S is a minimum. Excuse me. S is minimized. Now, by looking at the nature of this function, it is easy to see that the minimizing choices of alpha and beta will be obtained when the first order derivative of s with respect to alpha and beta are equal to 0, because here it is a squared quadratic function in both alpha and beta, that means it is a bowl shaped function, and therefore, the minimization will be occurred when the first derivative is 0. So, del s by del alpha, that is equal to minus twice sigma yi minus alpha minus beta xi is equal to 0, which we can write as sigma yi minus n alpha minus beta sigma xi is equal to 0, or we can write it as y bar is equal to alpha plus beta x bar. That is the first equation. Second equation is obtained by del s by del beta equal to 0, that means minus twice sigma yi minus alpha minus beta xi into xi is equal to 0. After simplification, this is resulting in sigma xi yi is equal to alpha sigma xi plus beta sigma xi square. Let me call it equation number 2. So, equations 1 and 2 are called normal equations. So, if we solve equations 1 and 2, then we get the least square estimates of alpha and beta. So, for example, if we solve it, we will get this solving 1 and 2, we get beta head is equal to syx by sxx and alpha head is equal to y bar minus beta head x bar. So, these are least squares estimates of alpha and beta. Here syx is sigma xi minus x bar into yi minus y bar, and sxx is equal to sigma xi minus x bar whole square. It can be shown that this alpha head and beta head are actually unbiased. Now, for that we have to make certain assumptions on the model. We have assumed that yi and xi are related through this relationship, and we have introduced a random error here, epsilon I. So, if we make epsilon i's are iid, and if I put normal 0 sigma square, then it can be easily shown that expectation of beta head, so that will be expectation of syx by sxx, that is equal to, now in this model sxx I can keep out, and when we are assuming here that epsilon i's are normal 0 sigma square, then yi follows normal alpha plus beta xi and sigma square. So, if we make use of this, it is related to expectation of syx. Now, let me calculate this syx term. So, syx is equal to sigma xi yi minus n x bar y bar. So, if I take expectation of this is equal to sigma xi expectation of yi minus n x bar expectation of y bar. So, that is equal to sigma xi alpha plus beta xi minus n x bar. Now, if I know the expectation of yi, if I substitute for each of them here, I will get expectation of y bar as alpha plus beta x bar. So, this term after simplification becomes n alpha x bar plus beta sigma xi square minus alpha n x bar minus n beta x bar square. So, this is becoming beta sxx. So, if we substitute this value here, I will get beta sxx by sxx, which cancels out, that is equal to beta. So, this beta head least square estimate of beta is an unbiased estimate for beta. Similarly, if I look at expectation of alpha head, that is equal to expectation of y bar minus beta head x bar. Now, expectation of y bar is alpha plus beta x bar, and expectation of beta head we have proved to be beta. So, this cancels out. So, the least squares estimators of alpha and beta are unbiased for alpha and beta respectively. We may also consider after substitution an estimate for sigma square in this model. we may put yi minus alpha head minus beta head xi whole square. What is this term? Our initial error sum of squares was yi minus alpha minus beta xi. Once I have estimated alpha and beta and I substitute, then this is my estimated value of yi. This small yi is the actual value which has been observed, whereas from the model I can estimate it to be alpha hat plus beta hat xi. So, this is actually the error sum of squares, which we call SSE. So, this is the value of this. Now, if I substitute this yi minus alpha head, so alpha head is equal to y bar minus beta head x bar minus beta head xi. So, this becomes plus here whole square. Let us simplify this term, that is equal to sigma yi minus y bar whole square plus beta head square sigma xi minus x bar whole square plus twice beta head xi minus x bar yi minus y bar summation with a minus sign here. I have taken the cross product term here. So, this is equal to SYY plus, now beta head is equal to SYX by SXX. So, this is SYX square by SXX square into SXX minus twice SYX by SXX into SYX. So, that is equal to SYY minus SYX square by SXX square, sorry SXX. Then it can be shown that this will have expectation of SSE divided by n minus 2, that will be equal to sigma square. So, this we call MSE, mean sum of squares due to error. This is an unbiased estimator. In modern statistics, this particular analysis is coming under the topic of regression analysis, where we study various kind of relationships between given variables. So, suppose we are given variables xi's and yi's, or x1, x2, xk and y, where y is the response variable and x1, x2, xk are the explanatory variables. Then we fit various kind of relationships between y and x1, x2, xk, and we derive the estimates of the parameters through least squares method. This methodology is also used for all types of linear models, including those which are used in the analysis of variance. So, we will not pursue too much about this in this particular discussion. Next, we consider the method of moments. This is attributed to Carl Pearson. The model is as follows. If we have a random sample, say x1, x2, xn from a population with parameter theta. So, theta may be in general 1 dimensional, 2 dimensional or k dimensional. So, here k is greater than or equal to 1. What we do, we consider mu I or say mu j prime, that is the jth central moment, sorry, non-central moment of distribution of p theta. That means if I say that x1, x2, xn is a random sample from here, that means expectation of x1 to the power j, that is actually mu j prime. So, in general these moments will be certain parametric functions. For example, I may have say mu 1 prime is equal to g1 of theta 1, theta 2, theta k. Mu 2 prime may be some function, say g2 of theta 1, theta 2, theta k. If I have k parametric function, k parameters, then I write up to kth. Now, estimate, let us write here, I define alpha j. So, alpha j I define to be 1 by n sigma xi to the power j, I is equal to 1 to n. That means the jth sample moment. If we consider this, let us write this system of equations as 1. Okay. Let the system of equations 1 have solutions. Say theta 1 is some function of h1 of mu 1 prime, mu 2 prime, mu k prime. Theta 2 is some function h2 of mu 1 prime, mu 2 prime, mu k prime. Theta k is equal to some function of mu 1 prime, mu 2 prime, mu k prime. In method of moments, we estimate theta I by theta I head, let me call it hi, and in place of mu 1 prime, mu 2 prime, mu k prime, substitute alpha 1, alpha 2, alpha k for I is equal to 1 to k. So, these are called method of moments estimators of the parameters. So, basically what is the philosophy behind the method of moments? I am estimating the jth population moment by the jth central moment, that is mu j prime is estimated by alpha j. So, whatever parametric function is coming to us for estimation, we substitute the corresponding, because the parametric functions will be some functions of the moments, and then whatever moment term is coming there, we simply substitute the corresponding sample moment there. So, in short, this is the method of moments. So, like we had seen that the least square estimates are unbiased, but in general we cannot say that the method of moments estimators, so I will use the word MMEs, in general they may not be unbiased. So, sometimes they may be unbiased, sometimes they may not be unbiased. However, consistency may be true. In particular, we have say alpha j, this is consistent for mu j prime. By the weak law of large numbers, this convergence is valid. So, if the functions h1, h2, hk are continuous, then theta I heads are consistent estimators for theta is. So, consistency may be true, and in most of the practical cases this may actually happen. However, unbiasedness is not guaranteed. Let me explain this method by solving certain example. You may see that many times this is extremely simple. Suppose I say x1, x2, xn follow Poisson lambda distribution. So, here you can see only one parameter is coming. So, we look at only the first moment, mu1 prime is lambda. That means, method of moments estimator for lambda is simply alpha 1, that is x bar. So, we had actually seen that x bar is here unbiased. In fact, it will be consistent also, because variance of x bar will be, expectation of x bar is lambda, and variance of x bar will be actually lambda by n, because the variance of a Poisson distribution is same as the mean. So, variance will become lambda by n. So, x bar is also consistent. So, you can see actually in many times this method of moments estimator may be extremely simple. Let me take another example. Say x1, x2, xn follow normal mu sigma square. Now, this is a two parameter situation. So, we will write two moments. So, mu1 prime is equal to mu. What is mu2 prime? Mu2 prime is mu square plus sigma square, that is the second moment. So, from here mu is equal to mu1 prime, the solution, and sigma square is equal to mu2 prime minus mu1 prime square. So, method of moments estimators will be, for mu it will be simply x bar, and for sigma head square this will be 1 by n, that is your alpha 2 minus x bar square, that is 1 by n sigma xi square minus x bar square, which we can write as 1 by n sigma xi minus x bar whole square. You can also write it as n minus 1 by n s square. So, it is not s square. In fact, you can see expectation of x bar is mu, but expectation of sigma head square is n minus 1 by n sigma square. So, this is sigma head square is not unbiased. Already I have proved that x bar as well as sigma head square, they are consistent. Let us consider, say, x following binomial NP. Now, if n is known, then you have expectation of x by n is equal to p. So, p head MME is simply x by n. However, if n is also unknown, there may be a situation where we do not know how many number of trials have been conducted in the binomial distribution, and then I have to estimate both n and p. In that case, then you may write the two moments. You write mu1 prime is equal to np and mu2 prime is equal to n p into 1 minus p plus n square p square. From here we solve for n and p. So, you can look at the solutions. The values will turn out to be slightly cumbersome. We get here p is equal to mu1 prime minus mu2 prime plus, so we may just write down the values here. P is actually NP, that is NP plus n square minus n, that is n into n minus 1 p square. So mu2 prime minus mu1 prime is divided by is equal to n into n minus 1 p square, and mu1 prime is equal to np. So this implies mu1 prime square is equal to n square p square. So we divide. If we divide, we will get mu2 prime minus mu1 prime divided by mu1 prime square is equal to n minus 1 by n, that is 1 minus 1 by n. This implies 1 by n is equal to 1 minus mu2 prime minus mu1 prime divided by mu1 prime square. This we can write as 1 by n is equal to mu1 prime square plus mu1 prime minus mu2 prime by mu1 prime square. So n is equal to mu1 prime square by mu1 prime square plus mu1 prime minus mu2 prime. Similarly, p is equal to, because from the first one p is equal to mu1 prime by n. So if n is already determined, we just substitute there. So mu1 prime divided by this, so that will give me mu1 prime square plus mu1 prime minus mu2 prime by mu1 prime. So method of moments estimators for n and p are, so for n it will become, now here I have taken only one observation x, so we simply substitute x square divided by, now this will lead to some peculiar problem which you can see, x square plus x minus x square. This cancels out, you get only x. If you put p, then you will get x square plus x minus x square divided by x, which is cancelling out, and you get only 1. This is leading to absurd situation. Now why this is coming? Since I have here two observations, two parameters n and p, it is not possible to estimate both of them with one observation. That means I need to take a sample here. So when n is known, it is all right that I use x by n, but if n is unknown, we need sample. So let me say sample is x1, x2, x capital N. So in that case, this situation can be resolved. So here the MMEs will be n head MME is equal to, now x bar square divided by x bar square plus x bar minus 1 by n sigma xi square, which we can also write as x bar square divided by x bar minus 1 by n sigma xi minus x bar whole square, and p head MME will be equal to x bar minus 1 by n sigma xi minus x bar whole square divided by x bar. So here you can see the form is quite complicated, and the question of checking unbiasedness etc. is ruled out, because we cannot actually evaluate the expectations of ratios of this type of functions. Consistency can still be considered, because x bar will be consistent for p, and for NP, that means if I consider x bar by capital N, then it will be consistent for P, etc. So, the consistency may hold, but the unbiasedness is totally ruled out. In fact, it cannot be even checked. Let us take another example. Suppose we consider a 2-parameter uniform distribution. In a 2-parameter uniform distribution, we have A and B as the parameters. Now, let us consider, say, first moment. Here the first moment is A plus B by 2 and the second moment is A square plus B square plus AB by 3. Now, many times you will see that when we have multi-parameter situation, the solutions of the equation may not be trivial, because the equations need not be necessarily linear. In general, they may be non-linear equations, as you have seen in the binomial case, and same thing is true in the uniform distribution case also. So, if you solve these things, you will get A as mu 1 prime minus square root 3 into mu 2 prime minus mu 1 prime square, and B is equal to mu 1 prime plus square root 3 mu 2 prime minus mu 1 prime square. So, the method of moments estimators are obtained by substituting alpha 1 and alpha 2 for mu 1 prime and mu 2 prime. So, I will get x bar minus square root 3 by n sigma xi minus x bar whole square, and B head is equal to x bar plus root 3 by n sigma xi minus x bar whole square. So, in fact, you can see that many times the form of the method of moments estimators may not be very convenient to handle. In fact, again if I ask here to check the unbiasedness, expectation of x bar may be A plus B by 2, but calculation of the expectation of this quantity is not that simple, and therefore, in general the method of moments estimator does not seem to give very nice looking estimates. In some of the situations, of course, like in the Poisson distribution case or normal distribution case, we got nice solutions, but in many of the 2-parameter or more number of parameter situations, that the method of moments estimators may not be always very nice. Let me take one more example here. Let x1, x2, xn follow gamma distribution, and I will consider 2-parameter situation. So, a 2-parameter situation gamma p alpha, where p is the shape parameter and 1 by alpha is the scale parameter. So, here mu 1 prime is equal to p by alpha and mu 2 prime is equal to p into p plus 1 by alpha square. So, once again, if you want to solve it, so we will get it as p square by alpha square plus p by alpha square. So, mu 2 prime minus mu 1 prime square is equal to p by alpha square. Let us take the ratio here. So, alpha is equal to mu 1 prime by mu 2 prime minus mu 1 prime square, and therefore, p is equal to mu 1 prime square by mu 2 prime minus mu 1 prime square. So, alpha head MME is equal to x bar divided by 1 by n sigma xi minus x bar whole square, and p head MME is equal to x bar square divided by 1 by n sigma xi minus x bar square. Notice here that if I had taken p to be known here, then the problem will be extremely simple, because in that case I can simply substitute in the first equation itself x bar, and the estimate of alpha will become p by x bar. However, if 2 parameter situation is there, the solutions are not straightforward to obtain. Let us take, say, beta distribution. x1, x2, xn follow a beta distribution with parameters, say, alpha and beta. Here mu 1 prime is equal to alpha by alpha plus beta, and mu 2 prime is equal to alpha into alpha plus 1 divided by alpha plus beta into alpha plus beta plus 1. Now, if we solve these equations, this is quite cumbersome, and the solutions turn out to be alpha is equal to mu 1 prime into mu 1 prime minus mu 2 prime divided by mu 2 prime minus mu 1 prime square, and beta is equal to 1 minus mu 1 prime into mu 1 prime minus mu 2 prime divided by mu 2 prime minus mu 1 prime square. So, substituting for mu 1 prime as x bar and for mu 2 prime 1 by n sigma xi square, we get the method of moments estimators as x bar into, so if I take this one, x bar minus 1 by n sigma xi square divided by 1 by n sigma xi minus x bar whole square. Similarly, beta head mme is equal to 1 minus x bar into x bar minus 1 by n sigma xi square divided by 1 by n sigma xi minus x bar whole square. In all these cases, you can see that checking of the unbiasedness is extremely difficult. In fact, they will not be unbiased. Of course, consistency may still hold in most of the situations if the denominator is non-vanishing. For example, here the x bar will be consistent for mu 1 prime and 1 by n sigma xi square will be consistent for mu 2 prime, and therefore, they will be consistent, but not unbiased. Same thing is true in the gamma case also, that these two will be consistent, as x bar will be consistent for mu 1 prime and sigma xi square by n will be consistent for mu 2 prime, but again they will not be unbiased. So, this leads to, and another thing that we are observing is that the calculation of the estimates is not in a very convenient looking form, although the distributions are not too complicated, because these are some of the basic distributions like gamma distribution, uniform distribution or beta distribution. So, the estimates are not looking very nice. Another thing could be that here we have seen that we have to write the number of equations equal to the number of parameters, but there may be some situations where this kind of situation may arise, like if I consider, say, uniform minus theta to theta, that means it is a uniform distribution on a symmetric interval, but we do not know the range of the interval, therefore, theta is unknown. So, here the problem is to estimate theta. If I consider the first moment, actually it is 0. So, this does not give us any information about how to estimate the theta. So, now if we go by strictly by the rule of the method of moments estimation, then this is not an estimable function then. However, some practical solutions can be given. We may look at mu 2 prime, that means the second moment, that is 1 by 2 theta, and we look at x square dx from minus theta to theta, then it is equal to theta square by 3. So, if we make use of this, then theta is equal to root 3 mu 2 prime, and we may use the method of moments estimator as 3 and 1 by n sigma xi square. So, this is not strictly in accordance with the method of moments, but anyway this can be considered as a practical solution. Similar kind of situation may occur in various multi-parameter cases, where one or the other of the parameter may not be directly coming in the form of the expectation there. Another method of estimation that was introduced in the first half of the 20th century is the method of maximum likelihood estimation. This was introduced by R.A. Fisher in 1922. The earlier methods, like the least square method, it is based on the data. That means, if I have x I, y I, and we write a relationship and then we estimate the parameter. In the method of moments, we look at the form of the distribution and we basically look at the moments. The moment structures are used. However, Fisher said that we should make use of the full probability model, because the moments structure does not make use of the full use of the distribution, because two different distributions may have the equal moments. Say first moment or second moment may be equal for two distributions, and still you may get the different estimates. So, the method of maximum likelihood said that we should look at the form of the distribution itself and make full use of that. So, let us consider a simple example. Consider an urn which has a certain number of, say, black and red balls. So, it is known that the number of black and red balls are in the proportion it is either 3:1 or 1:3. That means, we do not know which one are more numerous. So, if we say that there are n number of balls and x is the number of the black balls, then we do the proportion x by n may be either 1/4 or 3/4. So, now, so what is the problem now? The problem is that we want to estimate this proportion to know that whether blacks are more or the reds are more. So, let me denote P is the proportion of, say, black balls. Then P is either 1/4 or 3/4. Now, let us see how to frame a statistical inference problem and then an estimation problem from here. What we can do, we can take a random sample from the urn. So, let a random sample of size, say, n is taken from the urn, and let, say, x denote the number of black balls in the sample. Then you can write actually this distribution of x. Probability that x is equal to ax, that will be actually ncx p to the power x 1 minus p to the power n minus x, where x can take values 0, 1 to n and p can take value 1/4, 3/4. So, the parameter space is restricted to two values 1/4 and 3/4, and if we want to estimate that, then we have to conclude whether p is equal to 1/4 or p is equal to 3/4. So, let us work it out for a particular value of n. So, let us take, say, n is equal to 3. If I take n is equal to 3, then what are the various probabilities for this? on this side I will write down what is the probability of x is equal to x, and on this side I will consider the values of p is equal to, so what is the probability of x is equal to x when p is equal to say 1 by 4, what is the probability of x equal to x when p is equal to 3 by 4. And on this side let us take the various values of x. X can take value 0, 1, 2 and 3. So, since n is equal to 3, what is the probability that x equal to 0? That will be equal to 1 minus p cube. So, if p is equal to 1 by 4, it is simply 3 by 4 cube, that is 27 by 64. When p is equal to 3 by 4, 1 minus p cube becomes 1 by 4 cube, that is 1 by 64. What is the probability of x equal to 1? That is 3c1, that is 3 p into 1 minus p square. So, when p is equal to 1 by 4, this 3 by 4 square becomes 9 by 64, 9 by 16, and then you have 1 by 4. So, it becomes again 27 by 64. Whereas, this value will become, when p is equal to 3 by 4, then this is 3 by 4 and this will become 1 by 4 square. So, this will become 9 by 64. When x equal to 2, you will get 3 p square into 1 minus p. So, for p is equal to 1 by 4, this becomes 9 by 64, and for p is equal to 3 by 4, this becomes 27 by 64. For x is equal to 3, this probability simply becomes p cube. So, it is 1 by 64 and 27 by 64. So, as a layman, what will be our observation? Our observation is that when we have taken a random sample of size 3 from the urn and we observe that what this sample contains. So, we note down the number of black balls and the red balls. So, if we observe that there are no black balls, that means all the balls are red. The probability of that is higher, corresponding to p is equal to 1 by 4. That means, as a heuristic thinking, it will mean that there are actually less number of black balls. That means, p is equal to 1 by 4 is the likely value, or you can say most likely value. Similarly, when x equal to 1, then corresponding to p is equal to 1 by 4, you have a higher probability. That means, it shows that it is more likely that the number of black balls is less in the urn, because 3 times you have drawn and you are getting only either none or 1 black ball. Whereas, if you get all the 3 times a red ball, a black ball, then the probability is higher for p is equal to 3 by 4. That means, it is more likely that the number of black balls is more than the number of red balls, and the same observation is true when x is equal to 2 is observed. So, what we are doing? We are looking at the actual sample observed. So, what is the probability or what is the parameter value for which the likelihood of that sample being observed is highest? That means, we are looking at the maximum likelihood function. So, what is NCX p to the power x 1 minus p to the power n minus x? Actually, this is the probability mass function of the random variable x. Here, we consider p to be unknown parameter and x is the random variable. So, x, small x is the values of that random variable. Now, I am giving a different interpretation to this. I am calling it the likelihood function of this for different values of p. And I am looking at that value of p for which this is maximized. So, you can see that when x equal to 0 or 1, then I am taking p hat to be 1 by 4, and when x equal to 2 or 3, then I am taking p is equal to 3 by 4. Why I am taking these values? Because corresponding to these values, the likelihood function, that is this value, is actually higher. Now, this is the case which I explained through 2 points in the parameter space. If I have infinite number of points or more than 2 points, then we simply look at the maximum value over the entire parameter space. That means the problem is reducing to maximize this function, which I call the likelihood function. So, we introduce the term called the likelihood function of a sample. So, we call likelihood function. So, when the sample x1, x2, xn is observed, okay, corresponding to random variables x1, x2, xn, then the joint probability density function or probability mass function, that is f x1, x2, xn and the parameter, that is called the likelihood function, that is L theta x, where x is of course x1, x2, xn. Then the maximum likelihood estimator of theta is that value theta hat x for which L theta hat x is greater than or equal to L theta for all theta belonging to theta. So, basically it becomes a optimization problem. That means, we have to find the extremum points of the likelihood function. Now, for that we may use the methods of calculus or any other analytical methods. In general, we have seen that the parameter space will be an interval, and therefore, we have to use the usual methods of calculus such as differentiation, putting equal to 0, checking the second derivative or any other analytical method. Sometimes we may be able to tell straight away from the likelihood function, or sometimes we have to use this kind of analysis. Now, if you look at the form of the distribution such as binomial distribution, Poisson distribution, normal distribution, they are falling in the form of distributions in the exponential family. So, when the distributions are in the exponential family, a major term is coming actually as an exponent, e to the power something or something to the power something. So, if I take log of that, then that terms that which are coming as xi terms, they are coming in the linear form. Therefore, in most of the cases, it is more convenient to handle log of the likelihood function. So, we consider log likelihood, that we denote by small l theta x, that is equal to log of L theta x. In the beginning, we will consider the case when theta could be a scalar, and then we also consider the case when theta is a vector, for example, in the case of normal distribution, etc. And we will see that what are the solutions. And another point is that sometimes this method of taking the log, etc., may not be very convenient. In fact, it may not lead to a solution. In that case, we may have to use direct analytical methods for finding out the solutions of the likelihood function. A general method is like we differentiate. So, we write dl by d theta is equal to 0. This is called likelihood equation. So, there may be a situation where we will get a solution and sometimes the solution may not be there. So, we will see a result where we say that the likelihood function always has a solution. and we will work out these things. So, in the next class we will continue the discussion on the maximum likelihood estimators. We will see that what are the properties that these maximum likelihood estimators satisfy, and then how do they compare with the other methods like the method of moments estimator, etc.